student. I am Praveen Kumar from ABS Engineering College, Ghaziabad. In today's video, we are going to discuss torque and speed equations of DC motor. So first of all, we will find out a general relation between torque and power. So let us consider there is a wheel of radius r. This wheel of radius r, it is acted by a tangential force of F Newton, and due to this force, the wheel starts rotating at n revolution per second. So, work done in one revolution can be calculated as work done in one revolution is equal to the force multiplied by the distance. So, for one revolution, the wheel is to be rotated through its entire circumference. So, the applied force is of F multiplied by this distance 2 pi r. So, this is the work done in one revolution. Now, the work done on this wheel per second can be given as work done per second can be calculated as work done in one revolution, that is F into 2 pi r multiplied by n, where n is the speed of this wheel in revolution per second. As we all know, work done per second is the rate at which energy is consumed or power. So, the power can be given by this F 2 pi r into n. So rearranging all these things, this r into F multiplied by 2 pi n. We all know r into F is moment of force, or it is the torque. So P is equal to T, and this 2 pi n can be written as omega, where omega is the angular velocity of this rotating wheel. And it is the general expression with which we can relate power and torque of a rotating body. Now, from this general expression, we can easily relate torque and power as torque of a rotating body is T divided by its angular velocity, that is 2 pi n, where n is the speed of this rotating body in revolutions per second. And if this speed is considered in RPM, speed is in RPM, RPM stands for revolution per minute, then we can relate torque and power. This T is equal to 60 divided by 2 pi P upon capital N, where N is the speed in RPM, or it can be written as 9.55 P divided by N. So this is the general expression through which we can relate torque and power. Now, as we all know, the mechanical power developed in motor armature, this mechanical power developed in a motor armature is given by EB into IA. This is where EB is the back EMF and IA is the armature current. So corresponding to this mechanical power, we can define armature torque, which is given by TA, that is 9.55 divided by motor speed in RPM into P mechanical, where P mechanical is the mechanical power developed in motor armature in watts, or this 9.55 divided by capital N, this P mechanical is EB into IA. We all know this back EMF of motor is given by this relation P phi Zn upon 68. So using this relation of back EMF, the expression of armature torque becomes This TA is, sorry, this can be written as, wait a minute. Okay. This TA can be written as 9.55 divided by N. Now in place of EB, we can write this P phi Zn upon 60A multiplied by IA. So this 9.55 divided by 60, that is 0.159. This N cancels out with this N. We get P phi Z IA upon capital A, Newton meter. This is the expression of armature torque developed in the armature of a DC motor. From this expression, it is clear that the armature torque of a given motor is proportional to flux into IA. These are the two factors on which the motor torque depends. And if we have to reverse the direction of rotation of the motor, or we can say we have to reverse the direction of torque, then in DC motor, we can achieve this either by changing the direction of flux or by changing the armature current. If both these actions are applied simultaneously, then two reversing action will, or we can say this two negative makes a positive, and there will be no change in the motor direction or torque will remains unchanged. So if we have to reverse the direction of rotation or direction of torque, then either we have to change the direction of field current or we have to change the direction of armature current. So this is the expression of motor torque. Now, moving to the speed equations of DC motor. We all know this back EMF of DC motor is given by this relation P phi Zn upon 60A. So from this expression, the motor speed is directly proportional to the back EMF and inversely proportional to the flux. So these are the two main factors on which we can say the speed of a motor depends. Now, for DC shunt motor, DC shunt motor, first let me draw the line diagram of DC shunt motor. This is the motor armature. As the shunt motor, the field windings are connected across the armature. So this is the shunt field winding, and this is the supply terminals. So this is positive terminal, and this one is negative terminal. This is back EMF V. This is line current, which is divided into two parts. One is field current, and the current flowing in the armature. This is I. Now, in DC motors, the value of field current is given by supply voltage V divided by resistance of shunt field winding, which is constant for a given motor, as for a given DC motor, the supply voltage and resistance of field winding is constant. So for shunt motor, as long as the value of field current is constant, so we can say that the motor flux is not going to change. So in that scenario, phi is constant and the motor speed of DC shunt motor at two different conditions can be calculated by using this relation N2 by N1 is just proportionate to the variation of the back EMF EB2 upon EB1. As we are assuming this motor flux to be constant, or it can be written as, we all know relation EB can be written as V minus IA2 RA divided by V minus Ia1 R. So at any variation in armature current, we can find out the corresponding new speed of a DC shunt motor using this relation. Sometimes a special case is created in which a DC machine, in one case it is acting as a generator and in another case it is acting as a motor. So for a shunt machine acting in two different cases, then we can apply the speed equation as follows. Speed of generator divided by speed of shunt motor, that is equal to, in case of generator, we calculate generated EMF, and in case of motor, we calculate back EMF. So this is the speed equation for a for shunt machine which is acting as motor as well as generator. So these are the different speed equations which we used for a shunt motor. Similarly, for series motors, first of all, let me again draw the line diagram of series motor. As we all know, this is series motor means the field winding is connected in series with the, this is series motor. This is supply voltage. This is series field. This is back. For series motor, all the currents are same. Armature current is equal to the field current is equal to the line current. So, motor flux is proportional to IA. So, the speed equation for a DC series motor at two different values of armature current or field current can be written as N2 by N1 is equal to EB2 by EB1 multiplied by phi1 upon phi2. Or in place of this variation of flux, we can also put IA1 upon IA2. Or the same speed equation can be written as N2 by N1, that is equal to EB2 upon EB1 multiplied by IA1 upon IA2. That depend upon the condition whether we are provided with two different values of flux or two different values of armature current. Now, this speed equation is valid in series motor till the series windings are not saturated, or we can say prior to saturation of field. Means we are assuming that this armature current or field current is directly proportional to the flux. So by increasing flux, the value of armature current is also increasing. Now, after saturation of field winding, what happens once this field winding gets saturated, the flux is constant, and in this scenario, the speed equation of series motor can be applied as N2 by N1, that is equal to EB2 upon EB1. So this speed equation is almost similar to the shunt motor, and here the variation of flux is not considered because now we are working with the saturated field winding. It means with the variation of armature current, the flux is not changing. So in that case, the series motor actually depending upon the saturation state of the field winding has two different speed equations. If the motor is acting prior to the saturation of field winding, then the variation of flux or with armature current is considered, and in that scenario, either this equation or this equation is utilized in order to determine speed at two different values of armature current. But once the field winding is saturated, and after saturation, the variation of flux is not considered, and in that case, the speed equation of DC series motor is similar to that of shunt machine. So this is the speed equation after saturation, where the CB2 can be written as V minus IA2 RA plus RSC, where RA is the armature resistance and RSC is the resistance of series field winding. Similarly, RA plus RS. So these are the different types of torque and speed equations which we are used in case of DC motors. I hope you have enjoyed watching this video. These are the references which are used while making this video. Thanks for watching this video. Thank you.